So the way the club meetings will work is that it will be like every other week for about 60 minutes each meeting. Each club meeting will have a physics contest, then a physics presentation, then a physics contest, and then you're free to go after that. But if you want to stay, we also have post-contest discussion where you can learn how to solve the problems that you didn't get in the contest. Communication will be done through the group chats. I had to make 3 group chats because apparently you can only add 32 people to one iMessage conversation. But I'll send to all of the group chats, so you'll always be up to date. Before you go, try to make sure to fill out the following as soon as possible. There's a leadership position application form, meeting feedback form. Those are both in the shared Google sheet. And then there's the HP Club form, which is on that desk, and you need a parent signature for that one. So just fill those in as soon as you get a chance. Without further ado, let's get into the presentation today. Wait, can someone do the slides for me? I'll do that.
I would not trust everybody.
Which way? The one on the side?
Yeah.
Mr. Sun, does bi-weekly mean every other week or
Yeah.
twice a week?
Every other week. Oh, because bi-weekly. So this week's topic is atmospheric optics. By the end of this presentation, you'll be able to explain why sky is blue, why sunsets are red, and why the Mars sky is red, and more. Okay, so imagine you were talking to an alien, and they ask you why the sky is blue. How would you answer them? It seems like this is actually a pretty hard question to answer, right? Because if you look at this sun, it's like yellow and can you go to the next slide, please? If you look at the sun, it's like yellow and white. And if you look at space, it's mostly black. So why would the sky be blue? And why would the sunset be red instead of black or yellow? So you'll know the answer to these questions by the end of the presentation. But first, we have to review waves. Light is just oscillations of the electric and magnetic field. Using our eyes, we can detect these oscillations. That's how we're able to see. It's like ripples in water, but instead of the water moving up and down, it's oscillations in the electric field. Now imagine that we plotted disturbance of the electric field versus the position. You would get a graph which looks something like this. If you took chemistry or physics before, you might recognize it as just a graph of a wave. The wavelength is the distance between any 2 successive identical points on the wave, and the frequency is the number of wavelengths per unit time. The speed of light is, therefore, the speed of the wave is the number of wavelengths which pass per unit time multiplied by the wavelength. But, can you go back? The number of wavelengths which pass per second is just the frequency. Does anyone know what Greek letter we usually use to denote the wavelength?
Lambda.
Lambda. Yeah, so we can say that the speed of the wave, in this case light, is lambda times f. And it's 300, by experiment, we know that the speed of light is 300 million meters per second. It turns out that the speed of light is always the same. It doesn't depend on the wavelength or the frequency of the light. So we won't prove this fact, but you'll just have to take my word for it, because this fact is kind of hard to prove. You can Google why this is true later if you want. So since the speed of light is equal to lambda times f, and the speed of light is always the same, it's a constant. That means if lambda increases, then f has to decrease in order to keep lambda times f equal to a constant. And if lambda decreases, then f has to increase in order to keep lambda times f constant. We can say that lambda and f are inversely proportional. So now that we've reviewed the basics of waves, we can now talk about the phenomenon which causes the sky to look blue, called Rayleigh scattering. So how does the light go from the sun to the earth? First, the white light from the sun goes through space, but space is mostly empty, so it travels and it's not disturbed. But then it enters the Earth's atmosphere, which we know is filled with tiny gas molecules. These are gases in the atmosphere, like hydrogen, helium, nitrogen, oxygen, and other gases. It turns out that actually these gases scatter the light waves. So I've plotted two different light waves. One has a large wavelength on the left, and another one on the right has a smaller wavelength. The dots in the background of the picture represent individual gas molecules. The blue ones are not interacting with the light wave, and the black ones are interacting with the light wave. It seems like based on the image, it seems like the smaller wavelength wave interacts with more particles. There are more black dots here, while the larger wavelength wave is not interacting with as many of the particles. But more interaction means more scattering. So it seems like the shorter wavelength wave would have scattered more than the larger wavelength wave. And that's what I want you guys to notice. Can you go to the next slide, please?
Yeah, I did.
Okay. It turns out that actually the scattering intensity is proportional to 1 over lambda to the power of 4, which checks out with what we had before. Because if the wavelength is smaller, then the number in the denominator is smaller, and therefore the scattering intensity will be larger. And similarly, if the wavelength is larger, then the scattering intensity will be smaller. So given that violet light has wavelength approximately 400 nanometers and red light has wavelength approximately 700 nanometers, what's the ratio of the scattering intensities? If you go back one, I want you to do it yourself.
I know.
You can show it. So the scattering intensity would be 1 over the wavelength of violet light, which is 400 nanometers to the power of 4, and then divided by 1 over 700 nanometers to the power of 4. Because it's like 1 over 400 divided by 1 over 700. It's actually 700 over 400 if you write that fraction out. And if you take this to the power of 4, you get 9.4, which is approximately 10. So it turns out that violet light is scattered approximately 10 times more than red light. And what's the consequence of that? Why do I mention this? Can you go to the next slide, please? So let's consider what this diagram represents the light from the sun scattering the Earth's atmosphere. The light from the sun is white. It contains all the wavelength. It contains red light, it contains green light, it contains blue light. And it travels pretty freely through space because space is pretty much empty until it reaches the Earth's atmosphere, at which point it begins to scatter. And as we saw in the last slide, violet light scatters much more than red light because violet light has a much smaller wavelength. The wavelength of green light is somewhere in the middle, and it scatters somewhat. It doesn't scatter as much as blue light, but it still scatters more than red light. So that's what these arrows are showing. The blue/violet light scatters the most, and it goes in all directions. The green light scatters second most, and it goes in many directions, but not as much as the blue light. And the red light is unaffected, almost. It goes straight through the atmosphere. So if you're an observer on Earth, what color light would you see?
Blue.
Yeah, and that's why the sky is blue. But this is almost a satisfying explanation, but I have one problem with this. Actually, violet has the smallest wavelength and not blue. So why is the sky blue instead of violet?
Oh, it's too scattered. Maybe.
It's a good guess, but the reason that it turns out that actually mostly violet light hits your eyes, but you see blue because our eyes are more sensitive to blue than violet. Our eyes are not good at detecting very short wavelength light. Violet's at the edge of our visible spectrum. So even though the light which hits your eyes is actually mostly violet, we still see it as blue. We'll present one final piece of evidence for Rayleigh scattering. Consider this picturesque, beautiful sunny day. I chose this red circle and analyzed the color of the sky inside that circle using Photoshop. The results were red 47, green 114, and blue 191. So blue light is scattered the most, causing it to hit the observer the most. and then followed by green light, followed by red light. And this is a perfect evidence of Rayleigh scattering. The higher wavelength light was scattered the least, red has the highest wavelength, and the blue was scattered the most. There's one unanswered question though. Can you go back to that unanswered question? Why is the color of the sky not uniform? Why are some areas of the sky darker and others lighter? Like if you see here, this is a really dark blue, but then as you go near the sun, it seems like it gets lighter. And why is that? Why is it not the same color blue all throughout?
Light is scattered differently in different areas.
Yes, exactly. Let's talk about, yes, that's what I wanted to talk about on the next slide. You got it. We know that the scattering of light due to tiny molecules, like gas molecules, is described by the Rayleigh scattering. But it turns out that the scattering of light due to larger but still microscopic particles, think like water droplets in fog, is instead described by Mie scattering. Mie scattering treats all wavelengths of light the same. So in Rayleigh scattering, we know that blue light is more scattered than red light. It depends on the wavelength of the light. But Mie scattering doesn't care about the wavelength. It scatters all light the same way. And Mie scattering also produces a different shape than Rayleigh scattering. Rayleigh scattering is pretty even. But Mie scattering, if the direction of light is this direction, it will create an intense forward lobe. So that's more intense forward lobe is why the sun looks like this on a foggy day. Because the fog is formed by a bunch of microscopic water molecules, which are bigger than gas molecules, but still really small. The rays are, due to the Mie scattering intense forward lobe, create these brilliant rays emanating from the sun. And that also explains this photo and why the color of the sky is not uniform. Near the sun, the intense forward lobe of Mie scattering is pointing directly at your observer. And that's why the blue light gets mixed with white light, and you get a lighter blue color. But away from the sun, the Mie scattering is not as present, and therefore you get a lighter blue color. You get a darker blue color, I'm sorry, because there's less white light mixed into it. So now that we've talked about what Rayleigh and Mie scattering is, we can just apply them to understand why sunsets are. Consider the light. This diagram represents a sunset, and you should consider the light which reaches your eyes. Having a longer wavelength, the red light is how does the Rayleigh scattering scatter the red light? Because the red light has a longer wavelength. Is it scattered a lot or scattered a little? Very little, yeah. And having a shorter wavelength, the blue light is like. Does Rayleigh scattering prefer to scatter longer wavelength or shorter wavelength light? Shorter. Yeah. So having a shorter wavelength, the blue light is mostly scattered by Rayleigh scattering. So by the time the light goes from the sun all the way to you on the earth, most of the blue light and the green light has been scattered out because they have shorter wavelengths, and leaves only the red light behind. That's why you see a red sunset. So just to recap, the sky is blue because blue light is scattered towards the Earth by tiny molecules in the Earth's atmosphere. Sunsets are red because blue and green light are scattered before being able to travel all the way to the Earth. Rayleigh scattering is the phenomenon where tiny particles like carbon dioxide, nitrogen gas, oxygen gas, and so on scatter light. Blue light being scattered the most and red light being scattered the least. And Mie scattering is the phenomenon where larger particles like water droplets in fog scatter light, with all wavelengths of light being scattered equal. A bonus question that you can think about is, what color is the sky of Venus, which has a thinner atmosphere than the Earth? What is it?
Redder.
Yeah, it's redder, right? Because not all the red light gets scattered out. Yeah. You can look up photos of Venus taken by space probes if you're interested. Okay, any questions? Please ask questions if you have any. Okay, thank you for listening. Yeah.
You wanna go to the next slide?
What?
I'll go to the next slide.
Yeah.
Sorry, I'm fucking bad.
Problem 1. If you want to try the problem yourself, pause the video now.
Let's draw an image of the flagpole and the ground. Suppose that this is the ground, and suppose that this is the flagpole. The flagpole makes a right angle with the ground. Let's suppose that the height of the flagpole is h. We are given that when you pull the rope straight down, it's 3 meters longer than the pole. It would look something like this. This is 3 and this is h. Therefore, we can write that the length of the rope, L, is equal to h plus 3. We're also given that when you pull the rope taut, it's 5 meters from the base of the pole. It would look something like this, where this is 5, and this is the length of the rope, which also equals h plus 3. We can now solve for h using the Pythagorean theorem. You can cancel h squared, and you get that h is equal to 8/3, which is the answer. Problem 2. If you want to try the problem yourself, pause the video now. Let's draw images for the two scenarios. In the first scenario, a flagpole 3 meters tall casts a shadow 5 meters long. In the second scenario, a tree whose height we don't know casts a shadow which is 62 meters long. We want to find h, the height of the tree. Notice that the tree and the flagpole are close to each other. Thus, the angle theta is approximately the same for both triangles. That means the triangles are similar. So we can write that 3 over 5 is equal to h over 62. That means h is equal to 186 over 5. Which equals 31.2. And that's the answer. Problem 3. Pause the video now if you want to try the problem yourself. Let the speed that the car is moving at be v, and let the time that you glance out the window be t. We want to find the quantity vt. In this case, v is equal to 88 kilometers per hour, and t is equal to 1 second. Vt is equal to 88 kilometers per hour times 1 second. This is the same as 88 times 10 to the third meters, since there are 1,000 meters in 1 kilometer, over 3,600 seconds, because there are 3,600 seconds in 1 hour. This is equal to 24.4 meters, which is the answer. Problem 4. Pause the video now if you want to try the problem yourself. We're given that f times lambda is equal to c. Therefore, f is equal to c over lambda. C is equal to 300 million meters per second. Lambda is equal to 700 nanometers. 10 to the 9 nanometers equals 1 meter, because there are 1 trillion nanometers in 1 meter. So in the denominator, we can write that lambda equals 700 times 10 to the negative 9 meters. If you plug this into your calculator, you'll get that frequency is equal to 4.29 times 10 to the 14 seconds inverse, which is the same as hertz. Problem 5. Pause the video now if you want to try the problem yourself. Admittedly, this problem was very poorly phrased, and I apologize for that. You are supposed to find the physicist's average velocity in 1 week, take the absolute value of that, and write that down as your answer. In order to find the physicist's average velocity for 1 week, let's first review what average velocity is. If a particle starts at position x equals x1 at time t equals t1, and then it ends up at position x equals x2 at time t equals t2, then the average velocity turns out to be x2 minus x1 over t2 minus t1. Notably, if the particle ends up back at its original position, then the average velocity is equal to 0, because x2 equals x1. Also, it doesn't matter what path the particle takes from x1 to x2. It can be any crazy path, as long as it ends up at x2. in this amount of time, the path doesn't matter. So in this case, we could say that the total distance traveled is equal to 4,000 kilometers, and the total time is equal to 1 week. So the answer is 4,000 kilometers over 1 week. Sorry for the poorly written question. Problem 6. If you want to try the problem yourself, pause the video now. First of all, notice that the horizontal velocity is constant until the diver hits the water. Second of all, notice that the time it takes the diver to hit the water does not depend on the horizontal velocity. Okay, so in the first scenario, we know that he traveled a distance d in time t. Let's let t represent the amount of time to hit the water. We have that d is equal to vt. Let's let x be the answer to the problem. We know that x is equal to the horizontal velocity, in this case 2v, times the amount of time it's falling, which is the same as the first scenario, also t. But that's also equal to 2d. Therefore, the answer to the problem is 2d. Problem 7. If you want to try the problem yourself, pause the video now. Let's draw the position versus time graph. Let's let y be the height of the ball. We know that the slope of the position versus time graph equals the velocity. Initially, the velocity is 0, so the slope should be 0 initially. We also know that the velocity is increasing because the ball is constantly accelerating due to gravity. Therefore, the slope should be decreasing on this graph. So the graph must be convex up. It turns out that the shape of this graph is actually a parabola, and you can verify that by writing the projectile motion equation. But we accepted any answer that was convex up. Problem 8. If you want to try the problem yourself, pause the video now. We will use energy conservation. The kinetic energy of a particle of mass m moving at speed v is k equals 1/2 mv squared. Also, the potential energy of a particle of mass m at height h above the Earth's surface is u equals mgh. This potential energy is due to the gravitational field. Because no work is done on the system of ball plus Earth, we know that the total energy is equal to k plus u, and this is equal to a constant. It doesn't change. Let's consider the potential energy of the ball at point P, point Q, and point R. We know that UQ is the largest because it has the largest height above the ground. Similarly, UP equals UR because they are at the same height above the ground. But because E equals K plus U is constant, if UQ is larger, then KQ must be the smallest. So KQ is less than KP equals KR, right? Because KP has to equal KR because UP equals UR. That means, and we know that the speed, K equals 1/2 mv squared. So that means that K is proportional to V squared. So V is proportional to square root of K. So if K is larger, then V will also be larger. That means that Q has the smallest speed and P and R have equal speeds. Thus, the answer is D. Problem 9. If you want to try the problem yourself, pause the video now. A common wrong answer to this problem is 50 kilometers per hour. By the end of the solution, you'll realize why it's wrong. Let's let the length of the hill be L. Now, in general, you know that distance is equal to rate times time. So when the car goes up the hill, we know the distance it travels is L, its rate is 40 kilometers per hour, and its time, let's call it T1. And when it goes down, its rate is 60, it travels the same distance D, and let's call its time T2. From these two equations, we know that T1 must be greater than T2. At this point, we can try to draw a velocity versus time diagram. We know that when the car goes up the hill at first, is moving at a slower speed of 40 kilometers per hour. And it's doing this for time t1. And then it increases its speed when it goes down the hill. It's 60 now. And it does this for a shorter time, t2. The average speed then is equal to 40 t1 plus 60 t2 over t1 plus t2. It's equal to this total area, which is equal to 40 times t1 for this rectangle, plus 60 times t2 for this rectangle, divided by the width, t1 plus t2. We also know that t1 is equal to L over 40 from this equation, and t2 is equal to L over 60. Plugging that in, we see that this is equal to 2 over 1 over 40 plus 1 over 60. This is equal to 48 kilometers per hour, which is the answer. But we can actually say this more generally. Let's suppose that our car went on a trip, and it used a variety of different speeds during the trip. Let's call the speeds that our car used during the trip A1, A2, A3, and so on. For each of them, the car went along this road of length L. So like first the car went across the road of length L at speed A1, then it came back at speed A2, and then so on. So in general, on the ith time the car crosses the road, the amount of time it takes is equal to the length of the road divided by the speed on the ith trial. So Ti is equal to L over Ai. And the average speed is equal to A1 times T1 plus A2 times T2, and so on to AK TK over T1 plus T2 plus etc. plus TK. This is just a generalization of this formula from the case when K equals 2. We know that Ti equals L over Ai though, so that means the numerator just simplifies to L, and the denominator simplifies to 1 over A1 plus, the numerator simplifies to K. Denominator simplifies to 1 over A1 plus 1 over A2 plus etc. plus 1 over AK. This is called the harmonic mean of one of the numbers A1, A2 through AK. Problem 10. If you want to try the problem yourself, pause the video now. Let's draw the free body diagram for the sled. We will draw the forces on the sled. A force of 92 newtons is applied to one direction, and the force of 90 newtons is applied in the other direction. Let's arbitrarily choose the right to be positive. Then we can say that the net force on the sled is equal to 92 minus 90. I said positive 92 because right is positive, negative 90 because left is automatically negative, since I chose right to be positive. We know that F is equal to mass times acceleration. Here the mass is 25 kg, and the acceleration is what we want to find. Therefore we know that A is equal to 2 newtons over 25 meters per second squared. This equals 25 kg. This equals 0.08 meters per second squared. Problem 11. Pause the video now if you want to try this problem yourself. The key observation in this problem is that the net force on the spring must be 0. Why is that? Suppose, for the sake of contradiction, that the net force on the spring is not 0. But Newton's second law tells us that force is equal to mass times acceleration. We're given that the spring is light. In physics problems, when they say light, it's synonymous with massless. So m is equal to 0. But we know that F is finite. It's not 0, since the forces are unbalanced. That means that the magnitude of A must be equal to infinity for F to be finite. But that's not possible. Like, you cannot have infinite acceleration. Thus, we arrived at a contradiction, and so our initial assumption that there was unbalanced forces on the spring is wrong. Therefore, the forces on the spring have to balance. the net force on the spring is 0. Great. So let's say that the spring is exerting a force to the right, F, on mass m1. But because the forces on the spring have to be balanced, it must also be exerting an equal force F2, F, on the mass m2. We know that F is equal to m1a1, but this is also equal to m2a2. Therefore, a1 is equal to m2 over m1 times a2. If you plug this into your calculator, you will get the answer 2.148 meters per second squared. Problem 12. Pause the video now if you would like to try the problem yourself. Okay, let's suppose that the ball is thrown at an angle theta above the horizontal. We will use one equation from projectile motion. If you want to learn more about projectile motion, I recommend that you read chapters 2 and 4 of Physics by Halliday, Resnick, and Crane. This book is pretty easy to find online. We will use the assumption that the time in the air is proportional to the vertical component of the initial velocity v0. So the initial velocity v0 is like this, and its vertical component is v0 sine theta, and its horizontal component is v0 cosine theta. We will assume that the time in the air is proportional to v0 sine theta, but since v0 is a constant, we can just write that the time in air is proportional to sine theta. Now let's consider the horizontal position of the ball. The initial horizontal velocity is v0 cosine theta, and this horizontal velocity will stay the same during the entire flight. The horizontal velocity doesn't change throughout while the ball is in the air because we're ignoring air resistance. Thus, we can say that the horizontal distance traveled while it's in the air, let's call it d, is equal to the time in air multiplied by the horizontal speed, or horizontal velocity, which is always v0 cosine theta. And this is proportional to the time in air, which sine theta times cosine theta, because v0 is just a constant. So d is proportional to sine theta times cosine theta. That means we just want to choose theta in order to maximize sine theta cosine theta. Now remember from pre-calculus that sine 2 theta is equal to 2 sine theta cosine theta. That means that d is also proportional to sine 2 theta. This is maximized when theta equals 45 degrees. Thus, for a fixed launch speed v0, the optimal angle which maximizes the range, d, is 45 degrees. Problem 13. Pause the video now if you want to try the problem yourself. First of all, I denoted this angle theta and this angle phi. Now let's take our system as the car, and let's analyze all the forces acting on the car. First of all, there's gravity. Gravity acts on every single particle in the car equally, depending on the mass. But for the sake of analyzing the system, we can just say that gravity acts at the center of mass, because the car is not rotating. There's no torques on the car. So we can just say that gravity acts at the center of mass. There's also this tension force from the rope, which also acts on the system, the car. This tension force, we can also say that it acts at the center of mass. The reason is because the car is not rotating. So for the purpose of analyzing the system, we can just say it acts at the center of mass of the system. This is the tension, and the tension is 4,600 newtons, because the problem asks for the greatest distance the car can be towed. In order to tow the car the greatest distance, you would want to maximize the tension in the rope without breaking the rope. So we can just say that T equals 4,600 newtons. Now, let's draw coordinate axes which are parallel and perpendicular to the inclined plane. This is the most convenient choice. Okay, so this angle will be equal to theta because of similar triangles, and this angle will be equal to phi. Now we can write the forces in the x direction. Let's call this the x-axis, and I will choose the convention that this direction is positive x. So the forces in the x direction are equal to the component of the tension in the rope in the x direction. It's equal to t cosine of phi. But then there's also gravity, which is pushing the car down the ramp. The component of gravity in the negative x direction is mg sine theta. And by Newton's second law, this is equal to the mass of the car times its acceleration. So we know that acceleration is equal to t cosine phi over m minus g sine theta. If you plug this into your calculator, we can plug it in because we know t, we know phi, we know theta, we know g, we know m. You will get that the acceleration is exactly 0.3872 meters per second squared. The problem asks us to find the greatest distance the car can be towed. So if you have motion at constant acceleration starting at rest, the distance is equal to, after t time, is 1/2 at squared. Here t is equal to 7.5 seconds. So if you plug the acceleration into this formula and you plug the time into this formula, the second squared will cancel and you'll just be left with the answer of 10.9 meters. Problem 14. Pause the video now if you want to try this problem yourself. This is actually a trick question because the thing is that half of the moon is always illuminated, no matter what phase we observe on Earth. Specifically, if this is the sun and this is the moon, then this side of the moon is illuminated and this side of the moon is dark. It does not matter what phase of the Earth we observe on the Earth. The amount of energy reaching it from the sun is always the same. The only situation where half of the Earth is not, or half of the moon, is not illuminated by the sun would be during a solar eclipse, where the Earth gets between the moon and the sun. And in this case, for a very short period of time, the moon is not illuminated at all. But clearly this is an extreme case and it's not what the problem is asking for. So this problem, the answer is B. About the same as at full moon. You are meant to recognize that the amount of energy which reaches the moon does not depend on what phase we observe. Always half the moon is lit up by the sun. Problem 15. Pause the video now if you want to try this problem yourself. Okay, in order to solve this problem, we need to realize that this is a position versus time graph. We know that velocity is the slope of the position versus time graph, and acceleration is the rate of change of the velocity. What does that mean? So between time A and time B, the velocity, aka the slope of the graph, is constant because it's a straight line. A straight line has constant slope. Hence, the rate of change of the velocity is 0. So here A equals 0. Similarly, between time D and E, the acceleration is also 0. Now let's consider the time between B and C. Here, the velocity is decreasing. Here, the velocity is the slope here, but over here, the velocity is this. As you can see, the slope here is greater than the slope here. That means that the velocity decreased. So that means that A had to be less than 0 because A is the rate of change of the velocity. Similarly, the acceleration between C and D is also negative. Now let's consider the acceleration between time E and a later time. Here the velocity is the slope of this line. And then a bit later, after E, the velocity is equal to the slope of this line. This line has a greater slope than this line. That means that the acceleration, aka the rate of change of the velocity, was positive. So here A is greater than 0. By similar reasoning, here between time 0 and time A was also greater than 0. Now all you have to do is imagine a roller coaster. Imagine you're at Six Flags and you're riding like a drop tower or some other really scary ride where you feel weightless for a while. suppose that this is your roller coaster cart. At what moment on the roller coaster would you feel weightless? It would be when you're plummeting. And when you're plummeting, if we choose this as the positive y convention, as they have done in this problem, then when you're plummeting, your acceleration is downwards due to the gravitational acceleration g. So your acceleration is less than 0. Your velocity is getting more and more negative as you plummet towards the ground. Your velocity is decreasing. Thus, you feel weightless whenever a is less than 0. And that's why the correct answer is that the 0g flight begins at B and ends at D, during which time the magnitude of a equals g and a points down. A is less than 0. This is also a good moment to talk about non-inertial reference frames. What is an inertial reference frame? An inertial reference frame is a frame which is moving at a constant velocity. But a non-inertial reference frame is one which is not moving at a constant velocity. It's being accelerated. So in this example, the roller coaster cart is a non-inertial reference frame, because when you're going down the hill, there is some acceleration on the roller coaster cart, specifically gravity, which is causing it to accelerate downwards. So let's go fully abstract. Suppose that I have some box, and you are positioned inside the box. For you, the entire world is just a box. You can't see anything outside of the box. Now suppose that the box accelerated downwards with some acceleration a. Inside your world, inside the box, where you can't see anything else, you would perceive a upwards acceleration of a. This is known as a fictitious force. And this is a very useful technique in solving problems. You can consider non-inertial reference frames, and you turn the acceleration of that frame into fictitious forces inside of that frame. Problem 16. Pause the video now if you want to try this problem yourself. To be honest, this is not really a physics problem. It's just a math problem. Let's draw a cube. Each side of the cube has length 3 meters. Initially, the cockroach starts at one side of the cube, and it ends up at the diametrically opposite side of the cube. We can use Pythagorean theorem twice. So first of all, this length is equal to square root of 3 squared plus 3 squared, because this is a right angle. So this is equal to 3 root 2. But we actually want to find the distance between these 2 points. So let's draw this line. Notice that this is a right angle, and this side has length 3. So we can apply the Pythagorean theorem again. 3 root 2 squared is 18, plus 3 squared is 9. And that gives the length of the so-called space diagonal of the cube, root 27, which equals 3 root 3. This is the answer. Problem 17. Pause the video now if you want to try this problem yourself. Some prerequisites to this problem are uniform circular motion and frictional forces. If you want to learn more about uniform circular motion and friction, you can read chapters 4 and 6 of Halliday, Resnick, and Crane. Okay, let's draw an image of what's going on. Let's call the radius of the circular room r. Now let's consider a single rider who is moving around the circle. We are given that uniform circular motion requires a constant inwards acceleration towards the center of the circle of magnitude v squared over r. So we can rewrite this actually. Let's call the angular velocity of the rider omega. That means that, so what is omega? If we measure the rider's position with respect to some fixed point, in this case let's measure the rider's position theta with respect to the vertical, then omega is the rate of change of theta. So, for example, if omega equals 2 pi radians per second, then the rider would complete 1 revolution per second, because 2 pi radians is equal to 1 entire revolution. Okay, so we have omega. And from the arc length formula, we know that v is equal to omega times r. Therefore, a is equal to v squared over r, but this is also equal to omega squared times r. So we will be using this from now on. These two are the same. Okay, now let's consider a side view of this person. So here we considered a top-down view. Now let's consider a side view. Let's model the person as just a rectangular prism. There's gravity, which is acting down. There's normal force from the wall. This normal force is what provides the acceleration towards the center of the circle. And finally, we know that the person is not moving, and the force is not moving down, and the force which balances gravity and causes them not to move downwards is friction. It's called the frictional force F. Now, you need to know that friction, in this case we have static friction, and the static friction force is equal to mu s, the static frictional coefficient, times the normal force. But what is the normal force? Remember that the normal force is what causes their acceleration towards the center of the circle. Because F equals ma, we know that n is equal to m times a. Here a is omega squared r. So now we can plug this expression for n into the expression for the frictional force. F is equal to mu s times m omega squared r. But also, we know what F is. We need the forces to be balanced because the person is not accelerating up or down. Therefore, the net force in the vertical direction needs to be 0. Therefore, F equals mg. So mg equals mu s times m omega squared r. We can cancel the m's. So notice that m completely disappeared from our equation. That means the frictional coefficient does not depend on the mass of the person. And now we can say that mu s is equal to g over omega squared r. Now we just need to plug in quantities. We know that g is equal to 9.8 meters per second squared. Omega squared, let's find what omega is. We're given that the room spins horizontally at 45 revolutions per minute, so we will need to convert units. We know that 1 minute is 60 seconds. And we also know that 1 revolution is 2 pi radians. Therefore, the actual value, therefore omega in convenient units is 3 over 2 radians per second. Finally, we know that the radius is 4 meters. If you plug this into your calculator, you'll get that the coefficient of static friction is equal to 0.11. This is the smallest possible coefficient of static friction for which the person will not slide down the wall. Problem 18. Pause the video now if you want to try this problem yourself. Okay, we are given that the time derivative of the position, aka the velocity, is equal to the position itself. That means that, for example, if the ball is at position x equals 1.3 meters, then its velocity is equal to 1.3 meters per second. And similarly, if it's at like position x equals 3.5, then its velocity is equal to 3.5 meters per second. Okay, but we know that the velocity is equal to the rate of change of position, so we can write v is equal to dx dt. So now let's write this equation. dx dt is equal to x. Let's multiply both sides by dt and divide both sides by x. So we get that dx over x is equal to dt. This is called separating the variables. I want all the x's on one side and I want all the t's on the other side. I also want the dx's and the dt's in the numerator. Why do we want that? Well, it's because now I can integrate. I will integrate from the initial position x which is x equals 1 meters, all the way to the final position, x, which is x equals 10 meters. I'll also integrate on the time. The initial time, let's call it 0, and let's call the final time tf. Notice that I use a different variable, tf, compared to dt, because the variable of integration, in this case t, should be different from the variable for the bounds of the integral. This helps you avoid confusion. So on the left, I would have log of x, because log x is the integral of 1 over x, evaluated from 1 to 10, should equal t, evaluated from 0 to tf. Therefore, natural log of 10 is equal to tf, and the natural log of 10 seconds is the answer. Problem 19. Pause the video now if you want to try the problem yourself. Okay, Archimedes' principle says that the buoyant force is equal to the weight of the displaced water. In this example, the block weighs 7 pounds. And then it's put into the water, and now the reading on the scale weighs 3 pounds. So we know that there must have been a 3 pounds buoyant force upwards applied to the block. That means that the weight of the block was also equal to 3 pounds because of Archimedes' principle. Okay, so now I've drawn images of what's going on in all 3 situations. In the first situation, it's just a pool with no one in the pool. In the second situation, I've drawn the air mattress. So this entire area is the air mattress. Some of it is above the water, some other parts are below the water. The total area below the water is equal to V1 plus delta V1. V1 is just the, if you were not drinking from the cup while you were in the water, then only this part of it would be below the water. But since you are drinking from the cup and the water in the cup both have mass, then we need an additional volume. We need to displace an initial volume of water to increase the buoyant force. Let's let the mass of the cup be mc and the mass of the water in the cup be mw. Then we know that we can write the equation rho w, the density of water, times delta V1 times g is equal to mc plus mw. Because the mass of the displaced water is equal to rho w times delta V1, right? Because mass is equal to density times volume. And then we multiply by g to get the weight. And this has to equal, I made a mistake, this has to be g as well. So now we can cancel the g's from both sides of this equation. And we get that delta V1 is equal to mc plus mw over the density of water. Okay, great. Now let's do a similar analysis for situation 2. In this scenario, you've dropped the cup into the water of the pool. And now the water that was originally in the cup is going to go everywhere. So in this case, let's call the volume of the cup itself, because the cup has volume, plus the water in the cup, delta V2. And I want to calculate what delta V2 is. Okay, so recall that the cup has volume. Let's first calculate the volume of the cup. We know that in general, the mass is equal to density times volume. So if we want to find the volume, it's equal to mass over density. The mass of the cup is mc, and the density of the cup, which is made of metal, we can call it rho m, the density of metal. We also have to, also included in delta V2 is the volume of all the water, which was originally in the cup. Using the same reasoning, we can say that the volume of the water in the cup is equal to mw over the density of water. Okay, so now we have these two relationships. One is for delta V1 and one is for delta V2. I want to compare them, and once we compare them, we'll be able to determine in which situation did the water level rise more. Notice that mw over rho w is the same in both of them. But here we have mc over rho w, and here we have mc over rho m. Note that rho m is greater than rho w. The density of metal is greater than the density of water. You can have physical intuition for this, right? If you drop metal into water, it will sink, indicating that metal is more dense than water. But because you have a larger value in the denominator here, that means that mc over rho m must be less than mc over rho w. So therefore, delta V2 is less than delta V1. In this image, the amount of displaced water is greater. The amount of displaced water while you're sitting on top of the air mattress and holding the cup of water is greater than the amount of displaced water when you just drop the cup into the pool. That means that the water level rises less in this scenario compared to this scenario. And thus, that means that when you drop the cup into the pool, the water level actually goes down. Problem 20. If you want to try the problem yourself, pause the video now. In this problem, we will need both conservation of angular momentum and conservation of energy. You can read about both of these in chapter 16 of Halliday, Resnick, and Crane, Gravitation. Okay, so let's write the conservation of angular momentum expression first. Whenever we talk about angular momentum, you must talk about it with respect to some axis. In this case, I'm going to choose the axis to go straight into the page through the sun. I chose it to be here because the mass of the sun is much larger than the mass of the mote of dust. That means that as the mote orbits around the sun barely moves because the sun is just so much more massive than the mote. So this axis is stationary. Now we can write the angular momentum about this axis, and it will be conserved. So we know that the initial angular momentum is equal to mvr. And if we let this distance be r prime, and we let this tangential speed be v prime, then we know that mvr is equal to mv prime r prime. Now, if we cancel the m's, then we see that v prime is equal to r over r prime times v. We will use this later. Now we can write the conservation of energy. Let's let the initial energy is equal to 1/2 mv squared due to the kinetic energy of the mote of dust minus the potential energy of the sun-dust system, which is equal to negative gmm over r. But I know that the final energy is equal to the initial energy because energy is conserved. And the final energy is equal to 1/2 mv prime squared minus gmm over r prime. Okay, great. But we need to use that we are given that the particle begins with a very small tangential velocity v. What does that mean? Well, note that the kinetic energy is to the second order in v. So if v is small, then v squared is even smaller. And thus, it's safe to say that this term is almost close to zero. It's negligible. Also, we know that r is much larger than r prime. This is a consequence of the fact that r is much larger than r prime because v is really small. This is a consequence of the fact that v is really small. So that means that this term is much larger than that term. So therefore, this is also basically negligible. So then we can say that the initial energy is equal to 0. So that means that 1/2 mv prime squared, this expression equals 0. So 1/2 mv prime squared equals gmm over r prime. We can cancel the m's. So you get that v prime squared is 1/2 v prime squared equals gm over r prime. Now we can plug in this expression from conservation of energy. 1/2 times r over r prime v squared is equal to gm over r prime. And we want to solve for r prime. So we can just do the algebra. This corresponds to answer choice C.